So, this is a good one. I hope it's on your other game. So this is one of those lessons where it would separate me as a teacher either good or great. It takes it. This is a hard lesson to communicate. Okay. I hope you are actively with me. So here's the idea. First of all, I have constantly said area under the curve by rectangles. But the calculus way of saying that would be saying you're finding a Riemann sum. He constantly was looking for area under the curve using rectangles. So when I say Riemann sum, you think area under the curve by rectangles. Okay. So Riemann sums is synonymous with rectangles. Now we're going to be using right all day today. You'll understand why in a little bit. But if the first thing I need you to understand or reinforce is that if I use rectangles, I'll get error, but I can minimize that error. So for example, if I try to find the area under the curve here with only one right-hand rectangle, then that would mean using this side, the right side, using that for my height, and that, obviously, that big old rectangle would have way too much error. Where's the error? Shade the error, please. Wouldn't this all be error? Okay, because that's area that I'm getting from the rectangle that's not actually under the curve. With me? Okay. So what if you used two rectangles, equal subdivision? That might be here and over and there and over. Now shade the error. Okay? More error or less error? Less. In fact, isn't this here little block here how much error we just reduced by? We now don't have this much error. We got a lot less error. Yeah? Try n equal 4. Now, in terms of error here, I think you'll agree it's less. I hope you'll agree it's less, because really if you compare this guy to this guy, this was here, but now that's been lost. I don't have that error anymore. And this error was there in this guy, but now that error is gone. So I've reduced my error by quite a bit. Yeah? Now do 8. Okay. Got that? So the obvious point is that, what do you notice about the error as we use more rectangles? The error decreases. In fact, in calculus terms, you could say as n goes to infinity, the error goes to 0, and we start to approach the perfect area, or exact area. All right. Now the problem is, I don't want to do 8 rectangles by hand. That's gross. And so we need to be able to use our calculator effectively. So that's the next thing. But even with a calculator, you still need to know how to use it. So get out your calculator, and we'll use it in just a minute. But first, we have to get into, all right, what do we do with our calculator? I think I said this yesterday, but in case I didn't, these guys over here that are blinking, don't use those. Those are pre-calculus calculators in degrees. Use these guys over here that are in radians, right? Please. All right. Now then, just to remind you, so the calculator doesn't want a big string of stuff. A calculator wants something clean, so we're going to use summation notation. So the big idea is that we're getting the area by adding many rectangles, where that is what Greek letter? Sigma, standing for S is thumb, all right? The sum of many base times heights. Cool. Now, this isn't geometry. This is called analytical geometry. It probably doesn't mean a lot to you, but just for you to appreciate mathematics here. There's a huge step forward in about 1500s when they took this world of geometry over here, rectangles and squares and circles and all that stuff, and algebra over here, and they put them together so that no more is it just, here's a circle with a radius of 2, but they combine that with the coordinate planes so that you can actually write an equation for the circle that has lots of points. And so that idea of geometry plus algebra is analytical geometry. It's the foundation of all applied mathematics. Without it, we could get nothing. All right, so the idea then is we're going to take that normal geometry kind of idea and put it on the coordinate plane. So we're talking x's and y's then. The bases of those rectangles are horizontal changes in x. And the heights come from where do we draw our rectangles and where do we go? But we always go at some x, we first find the x and then go up to the curve and draw the height there, okay? Now the delta x, most people are cool where that comes from. How do you find the delta x? Number of, keep hearing triangles. Rectangles. So number of rectangles and what else? Okay, so total region width divided by number of rectangles. You could say that a lot of ways. You could say x end minus x initial over n. Some, when we get to the fundamental theorem, we'll call that b minus a over n, where b is the left, the right end point, and left end point of the region. All right. Depending on the problem, it might look a lot of different ways. You follow me? Delta x is all those. All right. Now the x sub I, that's far more complicated. So let's say that we started here, okay? Ignore this part, and I wanted to find this area, okay? So I'm going to call this x initial for the starting point of the region. Yeah? You could also call it, many people call it. Okay. Now, say a delta x is, about a couple tick marks. Now, this is my first x. And what goes into where I'm at? X1 would be determined by two things. Delta x, okay, how far I just went, right? And what else? Where you started, okay? So it's all about where did you start and how far did you go? So couldn't you say then that the first x is where you started plus 1 delta x? Yay? And if I were drawing right rectangles, that's actually the first one I would be drawing my height at. The next x, x2, now I could look at that two different ways. First of all, I could say it's like x1 plus a delta x, but that stinks. Instead, I want to tie it all the way back to the origin. So it's x initial plus 2 delta x. Okay. X3, therefore, is x initial plus 3 delta x's. And generally speaking, then, The ith, any vague x, is x initial plus I delta x's. Now that then is the general idea of the ith x at which you're drawing your height is the initial x, or where you started, plus however many delta x's you've gone over. The third rectangle you will have gone 3 delta x over, and so on. You would end at the end delta x over, because they're in rectangles. So far, so good? Okay, now if we use right-hand rectangles, then the first x at which we would draw the height is x1, and that is always going to be the first. Maybe we should do this here. Okay, so I think you'll agree that all these x's have x initial plus some number of delta x's. So the counter really is the I. 1 delta x over, 2 delta x over, 3 delta x over. Now if we draw in a right-hand way, isn't the first rectangle we're going to draw after going 1 delta x over? So I starts with 1. The last would be what number x? How many rectangles did I do? Not I. N. The nth rectangle is x initial plus n delta x's. Okay? Each time we go over delta x, that's a new rectangle. We're doing n rectangles altogether, so the last one would be n. So the last I is, I goes from, look at the highlights. Those are the i's, the counter. I goes from 1 to n. Oops, forward. Okay. We're not going to be using left, but just to get you thinking. Somebody genius in here. What would I go for in left rectangle? 0 to n minus 1. Well done. You're a lot of geniuses. Way to go. Okay. Now, that said then, I could take this, and this you probably want to put in a big old box because it's important. Sum of delta x, f at x sub I, in more detail, is the sum of many. Now the delta x's are cool. I think I'm going to keep that in my definition. But the x sub I comes from the initial plus some number of delta x's over. So I delta x's. Where I starts at 1, the first I into the function is 1, and the last one is n. All right, now, right now it's a lot of symbol pushing, and it usually goes better if you see an actual problem at work, all right? So if I said express the area under y equals x squared on 1 to 5 using the given number of rectangles, use your calculator to evaluate, then let's go with finding this idea and bypassing the expanded because of summation. Not because it would be hard to write 2, but because we're about to write 20. I don't want to write 20. You follow? What's delta x here? Delta x comes from doing what? 5 minus 1 over n, and in this case, that's 5 minus 1 over 2, or 2. So this should be 2. And what does that 2 represent in terms of geometry and graph? It's the base of each rectangle, or the distance you're going to go each time. Cool. The f at. Okay. Now, at what x we're going to draw the height depends on what 2 things again? Where you start and how many delta x's you go. So where do you start? 1. You start at 1, and how many delta x's you go is, well, it's going to count. 1 delta x over, that'll be I equal 1. Later on, we'll do 2 delta x. That would be I equal 2. I represents the x at which you're drawing at that point. And what is delta again? 2. All right. What does I start with? 1 and ends at 2. All right. Now, throwing this into your calculator. Depending on how ugly the function is, I might put the function in F1 in the graphing menu, but x squared is pretty clean, so I don't know if that's necessary. Instead, I'm just going to type this as I see it. Now, this summation notation is here. Use this submenu, or catalog of functions. And then you're going to go a little summation there, you should see. And so if I do that bad boy, it pastes in the summation. Pretty cool. Write it in just as you see it. So H-A-J-K, is that H-I, starts at 1 and goes to 2, all right? And in the summation, we're going to go, what again? 2 times, and f at, what was it? You want to type in the function in f, or should we just type in the function square? Let's just type in the function. All right, so for the function is to square, yeah? And what goes in that function? 1 plus 2 I. Are you down? I'll give you a second to do that. Hit enter. And you get 68. That seems really large. Is that okay? That's bigger than I expected. Y equals x squared. From where to where? Oh, I guess that makes sense. Wouldn't you agree that let's just check that. That's, the first is height at 3, which is, what's the height at 3? 9. And what's the height at 5? 25. So I guess that does seem right. It's 68. We're okay. Just freaked me out. It's that big. We're cool. Yes? Why did I use?
Why wouldn't you use 5? So you use 2. Like at the very top.
Here? So that doesn't represent the end of the region. It represents the end of I. And so in, where's all my erasers? That's a good question. Thank you for asking questions, because this is going to get kind of wacky, and your understanding is totally predicated on you asking good questions. So the first x in is 1 plus, each of these deltas is 2. Do you agree? So we're going to go, the first x in is to start at 1 and go 1 delta x over. And the second x in is 1 plus, and that's 2 delta x's over. That's why I'm using 3 and 5. Now, let me answer your question here. Those are i's. Those represent how many deltas you've gone over. And in summation notation, this here, that's the first I used. And I think you'll agree that the first one we used was an I of 1. This here is not the end of the region, it's the last I used. And the last I we used was 2. That's why it's 2, not 5. Does that make sense? Okay. All right. Now, if you want to go more exact, so this was 68. Okay. If we want to go more exact, we could use 5 rectangles. I'm going to bypass that general summation and go to the specific. If n equals 5, then I'm going to do, n is the number of rectangles, I just is the counter as we go. First rectangle, second rectangle. So we would start with a first rectangle and end with
How many rectangles? So what is the top of the summation? 5, okay. What's delta x now? Is delta x going to change if I go more rectangles? Yeah, it should get smaller if I use more rectangles. So what is delta x now? The total region is 4 divided by 5, 4/5. All right, so delta x is 4/5. And f at what x will I calculate my height? Start plus deltas. Start is still 1 plus, what's each delta? 4/5 and some number of times. It could be I times 4/5 or 4/5. That is one fine code. That's mom's? No. Sure?
No, it's my neighbor's. It was a girl.
Okay, I just think. All right, I like it. It's cool. Right on. So, if you slap that into your calculator, would we expect this to be more or less? Less, because we're actually going to get less area, going to get less area. So if you throw that in your calculator, so sum 1 to 5, 4 divided by 5, and I need to create some squared parentheses. And in the parentheses, I need to put 1 plus, nope. One plus 4i divided by 5, something like that. I think I put that incorrect. I get 1,284/25, or 51.36. You down? Okay. This is 51.36. All right, it was less, like I expected. Cool. Now would you try the same thing for 20? What's delta x now? 120, sorry, it's 4 divided by 20, so I agree with 1/5. Cool. So my summation is from an I of 1 to an I of, the top represents how many, and in this case we're doing from a first rectangle through the 20th rectangle, adding them all up, 1/5 of f, or 1/5 times f of 1 plus 1/5 I. Starting number plus however many delta x's you've gone over. I'm having a hard time reading here as a group. These, I obviously, based on my data understand. What about everybody else? We doing well? Yes. For right-hand rectangles, I will always be 1, and so you can expect that to stay that way. I'm not going to. Left and midpoint is up big enough, so we're just going to keep it pretty close. Yes, I will start at 1 for quite a while. So, throwing that in your calculator, you'll get quicker and quicker at this, but the point is, I wanted you to do this at least 3 times because I wanted you to get tired of writing this in. Not because I want to waste your time, but because I want you to say, gosh, there's got to be a better way. It's 1 plus 1 I divided by 5 squared. I got 1,094/25. Decimal approximation is 43.76. Do you concur?
Yes.
Okay. That's 43.76. All right. Now then, we are going to eventually develop this more generally speaking. So, what if I just said, you know what, let's just say n is anything. N. You just leave it in. What's delta x? 4/n. We're not gonna actually divide by some number. We're just gonna say 4 divided into n chunks. all right? What does the summation start at and end at? N, okay? And the delta x is now? And the height will be f at?
1 plus 4 over
Beautiful. See, now I'm getting some participation. All right. Now, instead of typing this over and over again, it would be cool if we could actually define some function that's like that, so we could just say, here's my function, do it at 7, and 10, and 20, and a million. So that's what we're going to now do. Define a sub n. Now this guy, that's a super important function button on your calculator in higher math. It's basically let a sub n be defined as this rule. Okay, this colon equals is right here. It's second above the 9. Now what I want you to do then is we're going to call this, I can't call it A because, actually maybe I can call it A. This I don't have anything, I had something stored as A, so I couldn't call it A. But I'm going to go A of n. All right. Now I'm going to do this colon equals, which is to say let this function be defined as. Do they use that in computer? I'm not a very computer person. Is that something in computers? Never. All right. Okay, let this be defined as the summation. What happened? Okay, the summation from I equal 1 to n. Okay, and then I need the delta x. What's the delta x? 4 divided by n, and then I open up some parentheses for the function, and what x did I evaluate the function at? Or generally 1 plus 4 over ni, or 4i all over n, whatever you like, it doesn't matter either way. And that needs to be squared. Are we cool? Are you with me? After you do that, hit enter, and it says, okay, I said, there's my function. I just defined a function so far. It didn't ask you to calculate it. Okay? Now let's verify that this is doing what we expected it to do. So looking back, we had an estimate with 2 rectangles earlier, yeah? So let's use our function to do 2 rectangles and make sure it's doing what it's supposed to do. So how do you reckon we call up a sub n? Or foot of ours, and you should see A. And you say, hey, I want to do 2 rectangles equals. Name is not a function. Oh, that's bad. Uh-oh. Oh, yikes. Did I type in this function wrong? Why does my function look so funky?
What should we use 4n times the function?
Oh, aye. So I don't know if that's the problem, though. I still feel like I did something wrong. Did you guys get a result?
Yeah.
Okay, so maybe it was that my function is just badly defined. My bad, sorry, I typed in my function wrong. I obviously didn't do 4 times. I did 4 divided by, because I'm dumb. I apologize. Let me catch up to you. Jeez. See, now I'm getting rattled. And 4 divided by n times parentheses 1 plus 4 I divided by n, all that squared. I forgot what?
You didn't put 1 for I.
Oh, thank you. Good call. Okay. All right, so let me make sure mine's working. It sounds like yours is working. Okay, so we got 68, which is what we expect to do. Okay, cool. Everything's going great. So, that said then, What if we, instead of 20 rectangles, we tried to get more? Now, don't go crazy. So there's always some guy that says, I'm going to do 1 billion. Well, the calculator still has to make all those calculations. So you're requiring it to make 1 billion calculations. It's a great calculator, but it will lock up into a constant loop, and it'll be done in a week. So don't go nuts, all right? Instead, let's try I would progressively maybe do powers of 10 out. 100 rectangles, oh shoot, I did. 100 rectangles is that, which is 48.8144. If you did 1,000 rectangles, you get that, which is 41.381. You should see the change being less and less as you go, and they should start to be the same through the hundreds and the thousands, and you're getting closer and closer and closer and closer, and boom. Okay, so it feels like it's starting to approach 41 1/3, maybe. You with me? Okay, cool. Now, let's go to seeing if you can do this on your own. Would you try, let's try just A all the way through on your own, and let's see how this goes. Yes? What did I just say? So, you gotta push the button. You have to
I wanted to see what happened.
Alright. Just like I got one daughter that says, don't touch that stove, it's hot, and one says, okay. And one says, don't believe, yep, Harper, gotta touch the stove. Alright, yes.
My bad.
So, usually I let the before, but it's not. All right, how we doing, people?
I got 16 times. I'm getting 0 now.
First, check your paper and pencil work. What'd you say for this? This is I equal 1, 2, n. What delta? 3 over n. What function?
1 plus 3.
Not 1. 2. 2 plus 3 over n I times, yeah? You're starting here at 2, not 1. You don't always start at 1. It depends on the case. Okay, so that's not good. Okay, so your first estimate, I'm getting 108.515. Yes?
188.726. Mr. Pull that back up. You forgot you put in 3.
I forgot the 2 plus. Ay, ay, ay. Oh. Okay, how about 132.515? Still no?
3 over n. 3 over n times.
Ah, jeez. Okay, let's try this again. Boom, 33.128.
No.
Come on.
I got
Why not?
I got 188.
188, why? So do we agree with 3 over n?
Yes.
Do we agree with the function is I'm stupid? Sorry. The function is not 2 plus e to the, it's e to the 2 plus, yeah? 2 plus. I had the 2 in front of the e. The 2 plus is in the e. Okay, now let's try it one more time. I say 200. 200?
Yes.
Yeah.
Wait.
Hey,
The I starts at 2. It starts at 2.
the I does not start at 2.
Yes, it does. It says it starts. It's 2 to 5. The region is
No,
2
no,
to
no,
5.
no. I doesn't represent the starting x. I represents the number of rectangles. And you start with 1 rectangle, and then you do 2 rectangles. This is not the starting x value. It's always 1. But I put, okay. Alright? So, you can see there are a lot of issues to work out. So, A of 4 is 200.457. Then A of 10 to see the better area. $163.233. Yes? And A at 50 is 145.297. how did the first one go? Okay. If it did not go well, then let me call you over or ask a friend to look over what you did. But otherwise, try the next one, please. What's your delta X on the second one? 3 over n again. Sorry, I should have varied it a little bit. Oh well. Was this cubed? Is that what the function was?
Yeah. Oh my gosh.
Okay, so, nope, I did it again. I keep doing the same thing.
You should just do the fraction template.
What? That's ridiculous. This guy? Well, maybe I should if I keep getting the same stupid. Alright, maybe you're right. Maybe I should adjust what I do. So, 1. That might be good advice. So you're saying go here for the fraction. Maybe you're right. 3, 4, plus fraction template 3 I over 10 third. Okay, so what do we do first? 4? Did I say 4 rectangles? Did you get 2025 over 64 or 31.640? Yay. What did I just say? 31.640? Okay. Now, obviously, the other ones are not meant to check whether you put it in right. If you got the first one right, then surely you put it in right. The others are there to enforce the idea that the more rectangles you start to spiral in towards the actual area. So those aren't there to waste your time. If you have the first one, surely your function is correct. I just want you to see what you're approaching. So at 10 and 50. So for 10, did you get something like 24.5025? Or 10 rectangles on the second one? And for 50 rectangles, something like 21.068. Okay. I assume that's their best estimate. All right? Now we have time for one more. Try another one. So, actually, I need to write this. What's delta x now? Pi over 3 over n or pi over 3n? Those are the same. That's pretty gross. F at 0 plus pi over 3ni, yeah? Wish I wouldn't have started that at 0, oh well. Okay. So this one I'm gonna do right the first time, darn it. And we said this is. Yeah, I like that flaction template. Good call, Starnes. Way to go. Good call. 3. Was it 3 or pi? Pi. Pi over 3n times tangent pi. Oh, shoot. Fraction template pi over 3 and leaving I up there. Okay, try 4 and let's see if you succeed at the end. I got 0.936. 0.936. Okay. Okay. So that actually, I didn't know. This is not your homework. We'll do this Monday. I don't have to talk. So if you've done 42 already, then you're pretty much no homework. But if you haven't done 42, I was not going to say that something okay? So you have to do 42 guys. Oh my God. I can figure out how to do this on a